Hi everyone. Let's talk about the limits of real function and how to catch the limit in the graph of the function and how you can test the limit using a table and finally algebraically including the sandwich theorem. If you have a function f of x equal to x squared minus 4 over x minus 2. Yes, I hearing you saying I have a problem at x equal to 2. Yes, I have a problem here. So the function will never be defined at x equal 2. But except this, you can graph the function. It is. So at x equal to 2, you have a hole over here. Okay. But the rest of the function, how you get a line? I know the line equation is a linear equation has a degree 1. Yes, this is a square difference. So x minus 2 times x plus 2 over x minus 2. So I cancel out this one with this one. I end up with x plus 2. So except x equal to 2, I can graph it as a line with the hole at x equal to 2. Now, if I come to the left, to the right of 2, I will reach this height, 4. If I come from the left of 2, I also reach the same height, 4. And this is, I call it what? Yeah, I call it the limit of the function. So I have two limits. Also in this case, the same. I have a problem at x equal to 2. But in this case, I cannot get rid of the 2 by factorization like the previous one. If I graph this one, I come from the left for x. I reach up here up to infinity, positive infinity. But when I come from the left, I reach the height here minus infinity, right? So when you came from the left, you call it left limit. When you come from the right, you call it right limit. This is a notation for the left limit. This is a notation for the right limit. Okay. The question here, they are equal. In this case, yes, they are equal. So there is a limit at x equal to 2. Okay. So the limit exists. Here, the right limit is not equal to the left limit because the left one up to positive infinity and the right one, sorry, up to negative infinity and the left one up to positive infinity. So the right limit is minus infinity, the left limit is positive infinity. Okay, so there is no limit, and I can say the limit doesn't exist. Okay, you can use Desmos uh, graphical calculator to graph such function. Now, I have this graph. How I can check there is a limit? Yeah, my problem at x equal to what here? Say this is minus 1. Okay. So I have a problem for the limit for this function described by this graph at x equal to 1. When I come from the right, I read this height, say this is 1, this is 2, minus 1, sorry, minus 2. So from the left, from the right, I reach minus 2, and also from the left, I reach minus 2. So the right limit equal to the left limit, and the limit. In this case, like the previous one, when I come from the right, I reach positive infinity here. When I come from the left, I reach negative infinity here. So the right limit is not equal to the left limit, so the limit doesn't exist. So in the first case, the limit exists and equal to minus 2. The second one, the limit doesn't exist because the right limit is not equal to the left limit. In this case, no. The right one go to the positive infinity and the left one going to also positive infinity. So yes, they are equal. and the limit is equal to infinity. This one is very important function. They call it stepwise function, and sometimes they call it each side one function. Okay. This function at a specific point, which here is 0, x equal to 0, you have a different shape to the right of x equal to 0 and another shape in the left to the 0. For all value of x less than 0, the function is equal to 0. But for all x equal to 0 and above, the function is constant, which is equal to 1. Okay? This is a unit step function. Your problem at x equal to 0. Okay? So if you come from the right, you reach this height 1. When you come from the left, you reach this height 0. So the function, the right limit is not equal to the left limit, and there is no limit. For this constant function, there is no x to check, right? This is a horizontal line. When y equal to constant, this is a horizontal line with the slope equal to 0, as we know. A slope equal to 0. Okay, so if you come from the left or right, you will reach the same height, which is a constant. So the limit is always the constant. So for this one, without thinking, yeah, this is 8, because this is a constant function and the limit at any point is equal to the constant. Now, if you have this graph and asking you limit of x tends to 2 for the function, where is 2? 2 is here. If I am come from the right to catch the limit of f of x, x tends to 2 from the right, this is positive. So I reach this height 2. When I come from the left to catch the limit, when x tends to 2 from the left for f of x, I catch the same height 2. So this one is equal to 2. Why? Because the right limit equal to the left limit equal to 2. Okay? But remember, the function is not defined at x equal to 2, right? So you may have a right limit and left limit, but you don't have a value of the function at this point, because this notation, x tends to a, it doesn't mean x equal to a. X very close to a, right? Now if I go for x equal to minus 2, here it is. The value of the function is equal to f at x equal to minus 2 is 3, right? But the right limit when x tends to minus 2 from the right for f of x is equal to what? This height is what? 2. If I go from the left, this is the left limit when x tends to minus 2 from the left for f of x. I need this height, which is 4, right? So the left limit is equal to 4. The right limit is equal to 2. So the right limit is not equal to the left limit. So this limit doesn't exist. Okay. At x equal to minus 3, my function is defined and is equal to 3. So f at minus 3 equal to 3. When I come from the right to the 3 limit, when x tends to minus 3 from the right, for f of x equal to what? This height is 3. When I come from the left to get the limit for x tends to minus 3 from the left for the function, the same height, which is 3. So the right limit equal to the left limit equal to 3. So this limit is equal to 3. This is how to check your limit in any graph of the function. Okay, I will leave this one for you. Can you do it? Yes, you can check this one yourself. Yes, be careful. When you have this arrow, it means you are going up. The far up is positive infinity. Okay? And the far down here is negative infinity. Okay? Go and do it. Let's start with finding limits using a table of the values of the function. If I have this function, which is linear function, so if I graph it, I will have a line, okay? And he would like you to check, yeah, approach is 4. This is, he doesn't say x equal to 4. Approach is, this is the arrow we use. It means approach is 4, right? So we have to approach 4 from the right, left, and from the right as well. So I get a value for x to the right to the 4. So this is to the left to the 4. So I get values less than 4, 3.99, 3.9, 3.5, 3. And I substitute here, plug this number here to find the function. And also I get values to the right of 4, which is 4.01, 4.1, 4.5, and sub-plug it here to find the value of the function. If you notice, when you close to 4 for the right and left, you catch the value of the function very close to what? To 10. So the limit for this one, when x approaches 4, is 10. Now, we have such function. So this is our function here, f of x. And I'm going to approach minus 3. So I approach minus 3 from left and right. So I have to get value less than minus 3 to the right to the minus 3. Okay. And plug it here to substitute and get the value of the function. Get another values for to the right, to the left to minus 3, minus 3.1. So when I approach closer to 3 to minus 3, I have this value. When I go close to minus 3, I go to this value. So roughly they are minus 0.5, right? So the limit of the function is equal to minus 0.5. So this is how to catch the right limit and the left limit using a table. You get the values to the right to minus 3 and you get a value to the left to minus 3. Okay, so the limit when x tends to minus 3 from the left, this is the value, and this value, this value is the limit for x tends to minus 3 from the right. Okay, so this is how it works. Now we know how to find the limit using a table. So we get values to the right of the one we are going to approach and to the left. What about this one? Here is our function. We approach minus 1 from the right and left. Okay. Here, you can do this one also using this table. I go from x to minus 1. So these values to, yeah, this is to the left of minus 1. And this value to the right to the minus 1. So I'm close here to, so here is a value, here is a value. But at minus 1, because the denominator here is 0, so the function is undefined. But I don't care about the function at minus 1. I'm approaching minus 1 to the right and left. So I catch roughly here, yeah, minus 2. So the limit is minus 2. This is roughly minus 2, which is closer to this one, minus 2. Now, if you have such, You approach 5 from right and left again. Yep. You get values less to 5, to the left to the 5, and you get values bigger than 5 to the right to the 5. Here, the function also is not defined at x equal to minus 5, because if you substitute by x equal to 5, you have undefined value because you divide it by 0, which is an undefined value. Now you approach this value and you approach this value. They are the same, but here is a negative and here is a positive. So yes, they are equal, but one of them is negative and one of them is positive. So this one doesn't exist. So be careful with this one. In this case, yes, this is 1000, this is minus 1000, and they must be equal. Now, use the table to have this practice done, okay, and take your time. So be careful. He said minus 2, so you go from right and left to minus 2. Here is 1, so go to right and left to 1 and get the limit. Let's go for the most practical one, which is compute limit algebraically. But before we go for this one, let's go for the properties of the limit. If you have a polynomial, we know polynomial. What does it mean, polynomial? This polynomial, we always have it like this. Yes, if you have a0 plus a1x plus a2x squared plus a3x to the power 3 plus blah, 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 an x to the n. So if you stop at n is the degree because this is the highest power. This is, we call it a leading coefficient, right? And this is the leading term. This is of degree, the polynomial of degree n. Now, if you have a polynomial, you don't have denominators to worry about dividing by 0. So to get the limit for the polynomial, you just plug in the value of you are going to approach it. So when approach x tends to a, just plug in x equal to a in your polynomial straightforward. Okay? If you have two function and you have a limit for these two function at the same point, x tends to a, if you multiply a constant to the function, you can take the constant outside. If you add or subtract two functions and you would like to get the limit, you can take the limit for separately and add and subtract the result. If you are dividing, you can distribute the limit over the numerator and the denominator. If you are multiplying, you can distribute the limit over the multiplication. If you have a power, you can get in the limit inside, okay, and get the power for the result of the limit. If you have n roots, you can get the limit inside the n roots. Now, let's go and do it. Yeah, this is a polynomial. I'm going to approach 2. So, straightforward, I'm plugging the value of x. So, this is 4 times 3, 12, minus 10, plus 4. So, you end up with 6. Okay. How to do this one? You can take the limit inside the roots. Now you have a polynomial inside the roots, so you can plug in the number. So 3, substitute x by 2. So you have 3 times 4, 12 minus 4. Okay. Here, you can distribute the limit over the multiplication, right, first. So you have a limit when x tends to minus 5 for the first part, and you get the limit for the root. Now you can take the limit inside. So you have two limits. Now you can substitute straightforward because you have a polynomial. So when you plug in x equal to minus 5, you have minus 5 for the first one. You have root square of 11 minus 5, which is root square 6 and minus 5. This is how it works. For here you can factorize this one, or you can plug in straightforward. You can plug in because you have no problem with the denominator if you plug in x equal to 3 straightforward. So yeah, I can distribute the limit over the division. So I can go for the numerator. Now I'm just with the number here, 3 to the power 3 minus 5 times 3 plus 4 over 3 square minus 2. So what do you have? 3 square is 9 minus 5 times 3 minus 15 plus 4. So you have 13 minus I have minus 2 over here. You have 30 is 9, 9 minus 2, 7. Okay. For this one, as I said, this is a polynomial. So you can plug in the number straightforward. So minus 1 cube plus 5 minus 1 square minus 7. So you have minus 1 plus 5. Because when you have a negative to the power, even power, you have a positive, right? So 5 minus 7 minus 7 minus 1 minus 8 plus 5, you have minus 3. You can check. Okay. For here, we cannot. If you distribute the limit, you have a problem with x equal to minus 3, because if you substitute minus 3 squares, 9, 9 minus 9, 0. So if you plug in, you have here 0 over 0, which is undefined value. How to get rid of this one? Using factorization. Let's go in this. So this is a limit. X tends to minus 3, x plus 3. Now you can, this is square difference, so my x minus 3 and x plus 3. You can cancel out this one to this one. You end up with the limit when x tends to minus 3 for only 1 over x minus 3. Now you can distribute this limit, so you have a limit when x tends to minus 3 for the numerator, and you have the limit for the denominator. This is a constant, so it's the same value. This one is a polynomial, so you can substitute by x. You have minus 3 minus 3, so you have 1 over minus 6. Okay. For this one, if you put x equal to 0, you will have 0 over 0, which is undefined value. How to get rid of this 0 here, down here? This is the most important one to get rid of it. So this is a complete square. Okay. How you factorize this one? Simplify this one. The square of the first one minus, because you have minus here, 2 times the first one times the second one, plus the square of the second one, minus 25 over x. Now, 25 positive cancel out with the negative 25. So I left over with minus 10x plus x squared over x. I can take a common factor in the numerator, which is x. Take x as a common factor, minus 10 plus x. Now you can cancel out this one with this one, and you end up with limit x tends to 0 for minus 10 plus x. Now this is a polynomial, so you can substitute x equal to 0, so have minus 10. This is how it works. For this one, yes, you can factorize, by the way. You can make this one as a square difference as root square x square minus 2 square over root square x minus 2. And this you can factorize it. You can cancel out this one with this one. Okay, I forget the limit. Okay. Now I end up with limit x tends to 4 for root square x plus 2. You can get the limit inside this one up to the up to the power rule, the limit rules. So I can get this one here plus limit x tends to 0 for 2. This is a constant function. Give me the same constant, whatever a is. Here you 0 root square 0, which is 0 plus 2, which is 2. Some people say it is better to multiply by root square x minus 2, is the same thing, but I prefer this one. Okay. Now I will leave you to practice this one, but before this one you have to know how to factorize the algebraic terms. How to factorize a polynomial. Okay. I will end up with a sandwich theorem. It is not a sandwich to eat. If you have a function between two functions, this is why we call it sandwich. Okay. By this graph, you have your function here in between two functions, the red one and the blue one. Okay. So if you can catch the limit of this outside two functions, the middle one will be the same limit, right? This is the sandwich theorem. Let's go for this one. Yeah, I know I can work out with this one. So if I take the negative one and the positive one, I will find cosine 1 over x in between these two, right? You can check by graphing, right? Okay. So this is a sandwich theorem. So K for the limit for this one. Yeah, so the limit when x tends to 0 for minus x squared, and the limit for x tends to 0 for x squared, okay, this one equal to 0, this one also equal to 0. So the limit of this one okay, is equal to 0. Okay. It's very clear here from the graph. If you graph this two function, x squared and minus x squared, you will find your function x squared cosine 1 over x in between these two. So the limit is equal to 0. Okay. Yes, this one, if, yeah, I can say x cosine 1 over x between minus x and between x. You can check by graphing this one, right? So I know the limit of this one when x tends to 0 is 0, and the limit when x tends to 0 for this one is equal to 0. So it's fair enough by sandwich theorem to say this is a limit when x tends to 0 for x cosine 1 over x should be 0. Okay? This one, yeah, x square sine 1 over x between minus x square and positive x square. Take the limit for the left one, minus x square will be 0. And take for the right one, so it will be 0. So the limit of this one will be also 0 up to the sandwich theorem. This one you can check your function x cubed sine 1 over x in between minus x cubed and positive x cubed. And you can check for sure the limit of this one when x tends to 0 is 0, and the limit for this one is also 0. So the limit of this one is 0. So the value is 0. Here, yes, I know sine x over x is in between minus 1 over x and positive 1 over x. If I get the limit for the left one, when x tends to infinity, I get minus 1 over infinity, which is equal to 0. For this one, limit when x tends to infinity for 1 over x equal to 1 over infinity, which is 0. Okay, so the limit of sine x over x is 0. Now you can practice this one. Yeah, check this one in between minus x to the power 4 and positive x to the power 4. This one you can check, and you can use a graph to check this one. Thank you.